All right, so this was the last slide we covered. So I'm just going to keep going through this introductory chapter, give you an idea at first what the course is going to be about, but then later on we'll talk about performance measurement techniques, and that's very important for the course because everything that we do from a computer architecture perspective is geared toward enhancing or augmenting performance. So we need to know how we measure that. What do we mean by performance? So that's a big part of the chapter later on. So I don't know if you heard the term Moore's Law. And so Gordon Moore, one of the founders of Intel in the late 60s, early 70s, he observed that even though semiconductor technology had been sort of being commercialized in the mid to late 50s from an integrated circuit perspective, and at first we could make semiconductor devices, so we could make discrete transistors, and that was great. That actually got us out of the vacuum tubes and into solid-state electronics, and that afforded us lower power, higher density of components. So instead of a vacuum tube that was maybe 2 inches tall by 3/4 of an inch in diameter, we were looking at a transistor that was perhaps 1/100th of that size and would dissipate appropriately 1/100th of the power. So that was great. So the next thing was how do we put several transistors on the same silicon substrate? So that's a different thing than just having a single solid state transistor. So how do we put several of them and they live on the same silicon substrate? So that became an integrated circuit. And that was invented around that time by Jack Kilby from Texas Instruments, and he actually got a Nobel Prize for that many years later. And that technology had been progressing through the 60s to the point that Intel was founded in the early 70s. One of the founders, Gordon Moore, observed that the way that semiconductor technology or integrated circuit technology had been progressing and the number of transistors and devices that we were able to put on the same substrate were such that that level of complexity was doubling about every 18 to 24 months. So every 18 to 24 months, you could put twice as many transistors on the same chip. And then you could have more functionality, more complexity, and so on. And he predicted that that was going to be the case for years to come. We're going to see where that starts deviating later on, which has happened already. But that gave us a huge growth through the 70s, the 80s, and the 90s. Pretty much we were able to follow what came to be known as Moore's Law in terms of device complexity. And you can see some of the things that we were able to accomplish. So doubling every 18 to 24 months, if you do the math, and you are a fan of powers of 2, you know how quickly things can get large. In this case, the number of transistors that we can put on a chip these days. So here we are. We have computers, and from the purpose of this course, we're going to have, strictly speaking about computers, 2 classes of computers. We got the personal computer, so everybody knows that, and we can have a desktop, we can have a laptop, and we can have servers. So servers are the type of computers that we network together on server farms, clusters, and so on, that are used on the server side. Now, these days, every type of computer interaction is sort of a client-server architecture where the server is serving requests by the clients. It could be your laptop uh, doing a Google search. So that would be a request. Your computer, your laptop would be the client, and the servers in the Google server farms are those that serve the request. But we're going to see that that's not really all we have these days. There is a lot of other gamma of computers which are depicted here, which are the embedded computers. I'll get to that. But we also have supercomputers, and supercomputers are high-end computers for the application of scientific computation. You can do complex computations like financial forecasting, economic forecasting, weather forecasting, scientific type of calculations in physics, biology, and so on. But the architecture of these computers can vary. You can do specific cluster architectures of servers. Some people actually have networked a lot of laptops and turn it into a supercomputer. It really depends on the software that manages those resources. So we have that classification as well. But the most interesting, the newest type of class of computers are the embedded computers. And that's actually the largest class these days because your cell phone is an embedded computer. It's a computer that has very specific application, in this case, to manage your cell phone, but the cell phone has inherited a lot of functionality that we didn't have very long ago. Just 20 years ago, the cell phone was just to make phone calls until Apple invented the concept of the smartphone and the ability to have a phone take pictures, do audio, have apps that can do all kinds of things, including productivity apps like reading, writing, spreadsheets, databases. You know, the same thing that you would normally do on a classic laptop or a desktop. Now, a lot of those things can be done on a cell phone. The only limitation really is on the human-machine interface because there's still a limited screen size and there's no keyboard and things like that. But the ability is there. And there are a lot of other embedded computers that are everywhere. So essentially, if you have a processor and you are not a server, a supercomputer, or a laptop, or a desktop, you are an embedded computer. And these days, that is the highest number of computers can be classified as embedded computers, and it's just going to grow because of things like the Internet of Things paradigm, where you're going to put what is called an edge computer with sensors and the ability to track and provide position and location, and all kinds of interesting applications can come of that. So when we talk about a computer architecture, now we have to keep all this spectra of computer classes in mind, from very simple, maybe super specialized, very power aware, embedded computer at the edge of the network, because they can be networked as well, all the way to the other end, which can be supercomputers. So we're going to be talking about the fundamentals of how to architect chips that can serve the building and the coming about of any of these types of computers. There are some charts in here that may be a bit dated, but it does show the trend. So this one goes from 2007 to 2012, and you can see the installed base of cell phones at the top. So those are what were not considered smartphones. So some people still use the flip phones, and you can see how about in the year 2010 the actual sales and the install base of smartphones surpass the PC, not including tablets, which is another type of somewhere in the middle of a laptop and and a sort of in the middle of a laptop and a cell phone or a smartphone. Although higher-end hybrids like the Microsoft Surface, they're really much more than tablets. I mean, they can behave with like a tablet very well, but they really compete very well with even high-end laptops. Not gaming that laptops, but laptops on the high end for productivity type of activities. So that gives you an idea how all these different devices are the dichotomy and the mix is starting to become more complex because of the usability and the use cases, while pretty much before let's say 2010, you had a clear cell phone, a smartphone, and the PC, at least according to this graph. Then this takes another view earlier and brings us all the way to this year, and you can see that the smartphones has just gotten even higher. So the smartphone is an embedded computer, and embedded computers, the dominant architecture for embedded computers is the ARM architecture, which started as a intellectual property company. They didn't sell anything physical. They just sold the intellectual property of the ARM core. So companies that were making products and chips could put this processor core in their products and reselling, and they charge a license and royalty for that. ARM since then has been sold to a Japanese company called SoftBank, but they keep the same business model, and core still exists. So in this course, we're going to be talking about the ARM architecture as an example to get across all the concepts that we're going to be discussing, because in reality it's the most pervasive architecture out there when you consider smartphones, even though some tablets and you could say that most PCs are using an Intel architecture, including the Apple computers these days. Up to some time ago, Apple used to make their own processor, but they're using Intel now. So you can see that by these numbers, ARM is definitely the most widely used architecture, and that's why we use it as an example here in this course, and also in some other courses throughout the curriculum. So this is another chart. I think you get the point. So there are a couple of with this new types of devices, not only the smartphone, but also on the server side, getting more efficient, easier to network. There are two use case paradigms that you need to keep in mind when we talk about computer architecture. So one, picking up on what I've been saying about the smartphone, is the personal mobile device. So that is the smartphone or the tablet. that has the ability to connect to the network. Maybe has a GSM modem, and you can connect with your tablet anywhere. You don't have to have necessarily Wi-Fi. But we know some things about these types of devices. They are battery operated. So you're going to see that we're going to discuss that power becomes a very important variable. So before this paradigm of mobile devices, power was sort of an afterthought. It was nice that it was low power, but the main thing is that it was fast, the performance, and then that it was low cost. So the main trade-offs were cost versus performance. Now we have this third variable in there, and it's really an optimization of not only cost and performance, but also power dissipation from a battery life perspective. And then the other sort of new use case paradigm is cloud computing. So we have seen a lot of software as a service business model. That is a new business model that is actually much more attractive to companies than the business model when you bought software and you got a CD or you download a file and you install it in your computer. They don't want to do that anymore. They want to do what is called software as a service, where the application is running on the cloud or on the web, and that's where you do your interaction with the servers, and the main application is running on the network, and your computer really just becomes a user interface device to get to that network. This also has brought us the ability to store data on the network, and also services that enable the creation of this software as a service applications for like AWS, Microsoft Azure, and the Google infrastructure as well. So these are new applications and use cases that have also put new requirements in the way that we architect computers when we think about the server side. So we have the classic personal computer, as we have known it, whether it's a desktop or a laptop, in the middle, but it's really losing its applicability other than as a user interface type of way of getting to the network for cloud computing. And then we have the personal mobile devices that can do more and more each time. So these are, with this background, these are the things that we're going to be discussing in this course. You're going to get a very clear understanding of how programs, let's say a for loop in a C++ fragment of code, how that eventually becomes a bunch of ones and zeros in actual signals that are making a circuit on a chip do what needs to happen to execute that for loop. And through the instruction set of the processor, you're going to start seeing how that entails that hardware and software interface through that instruction set. Then in this chapter, we're going to talk about performance and how can we improve performance. And of course, to improve performance, we need to know how to measure it. So we're going to define what performance is in a very formal way. And then we're going to define methodologies for measuring performance and tools for doing that. And then towards the end of the course, if we get to it, we may talk about parallel processing a little bit. That's the, but the bulk of the course is really discussing how a program uh, becomes or translates to the actual signaling that and the hardware that is going to enable the execution of those programs. So throughout the course, we're going to be relying uh, what is called 8 great ideas that have come about in this type of technology through the development of where we are today. Uh, we're going to be looking at Moore's Law. I talked about that a little bit already, and we're going to see how how it has materialized. We're going to look at that closer. And when it hit a wall, which we call the power wall, and what is being done about it, and how do we, where do we go from here? Um, we're going to be using conceptualization tools such as abstraction. Now, if you can imagine, we are talking about since the 60s how complexity has been doubling. So when you do that progression, the complexity is huge. However you want to measure it, if you want to measure it in terms of speed, if you want to measure it in terms of devices or logic gates, which is itself an abstraction on a chip, the numbers are very, very high. So that complexity being what it is, we need a conceptualization tool to be able to put our hands around the things that we want to learn and the things that we want to explain. So abstraction is that tool. We're going to be using that a lot. And abstraction is a conceptualization tool to just look at enough detail, enough level of detail to be able to do the work that we want to do. So if you're working on an architecture, you don't need to look at the transistors. You don't even need to look at the gates. You can work at higher level and just look at signal routing resources and arithmetic and logic type of units and just work at that level. You don't need to care how those units get built all the way to the physical level, which they eventually will be. So abstraction allows us to do to look at just enough detail to do the work that we want to do, whether it is understanding something or explaining something. The other great idea is what we call make the common case fast. What that means is if you're going to do an improvement or you're going to design in a way a computer system and you're going to be designing it for performance, you want to enhance the performance of the part of the or the resource that is used the most. In other words, if you have a system and one part of the system is used 80% and another part of the system is used 20% of the time only, in a way that they affect, in the way as measured by the way that they affect performance. Uh, if you double the performance of the part that is used only 20%, as a whole, that is not going to make as much an impact as if you enhance the performance of the part that gets used 80%, let's say only 50% instead of 100%. So identifying the usage patterns of resources in computer systems is very important because then that tells you what is that you need to focus to enhance performance and come up with better designs. That's what make the common case fast refers to. We're going to look at different ways of enhancing performance. So one is parallelism. So we have different levels of parallelism, but we're going to be talking, for example, at instruction level parallelism. So we're going to look at an instruction from the instruction set and see what are the resources that are being used by that instruction and which are the resources that are not. And the ones that are not, maybe they can be used by another instruction, and we can run two instructions in parallel. So that's a great idea that we're going to be discussing more, specifically in Chapter 4. Also, in Chapter 4, we're going to be discussing pipelining. So pipelining is a way of not necessarily getting our result faster, but getting the rate at which we get results faster. And sometimes, or most times, we don't care about a single result, we care about a stream of results. So the rate at which we get those results, even though if we just focus on one, it may take us the same time as without pipelining. But when we do pipelining and we look at the stream of instructions, we get that the rate at which instructions are being completed is much higher. So we're going to be looking at those techniques, and these are hardware level techniques that we will discuss in Chapter 4 as well. Another way of performing or enhancing performance is via prediction. For example, you're all familiar with if-else type of structures. If we could predict which way we're going to go on that if-else construct, if we could anticipate, we could start doing that part of the code before we actually know what the answer is. And if we are right most of the time, then that would enhance the performance. So we're going to be discussing predictive branching at the instruction set level. And another area in which we use performance or we use prediction is for caches in memory hierarchy. So that's Chapter 5. So if we could predict what is the section of code that we are using the most, or the section of data that we're using the most, and if we could put that code and that data on a faster memory, if we could put it in a faster memory, which would be limited because it's faster and therefore more expensive, but if we could use that subsection of faster memory to put the data and the code that we use the most, then we would see an enhancement in performance if we can predict accurately which code and which data is the one that we use the most. That is tied to making the common case fast. If we can identify what the common case is, then we can put it in the faster memory and enhance performance. So that is the underpinning of the ideas behind cache and multi-level memory architectures and hierarchies. So again, that's the hierarchy of memories, and then the dependability enhancement via redundancy. If we have the case that is the most known is RAIDs, or redundant arrays of independent disks. So all types of server farms use redundancy because the disk is used so much that they're basically wearing off faster. For example, Google, they go through thousands of disks a week. They have to be replaced just because they are used so much. So these are the ideas that we're going to be seeing here and there throughout the course, and they're very interesting ideas as we dig into them. All right, so a little bit more about Moore's law. I think that, as I said, about mid 60s, so Gordon Moore predicted this. And it really was, if you actually go back and you plot the complexity of the number of transistors per chip, you get very close. Actually, that law really maps very well. So let's go back to the first Intel processor. So remember, Gordon Moore was one of the Intel founders that got founded in the early 70s. The first processor had 2,300 transistors, ran at 1 megahertz. Since then, let's just look at some data points. 60 million transistors for the UltraSpark 3, that's in the late 90s. 42 millions for the Intel Xeon 2001. We look at 2004, 55 million transistors for the Pentium 4, and later on for the an HPPA 8500 processor, 140 million transistors. So if you sort of plot these dates and the number of transistors, you can see that Moore's law holds pretty well. So it's really about complexity, okay? It's not about the speed, because the speed can be, as we see, can be modulated by your power needs or how much power you can dissipate, because you can put a lot of complexity, and if you don't clock it fast enough, then your power can stay manageable. So it's really about chip complexity as given by the number of transistors that the number of transistors that are you can put on a chip. But however, it is correlated, because to put more transistors on a chip, you need to make them smaller. And once you make the transistors smaller, they get faster. They get faster because the gate is smaller, and then the gate capacitance is smaller, so they can switch faster. So it is somewhat correlated. Certainly, you can say that you could not run at a higher speed, or at the speeds that we run these days, had the transistor size as given by the gate or the channel, the electrical channel length, had not been reduced. So let's look about some of the how this has impacted processors. So logic capacity, so it increases about 30% per year. Performance has increased about double every 1.5 years. So it actually has followed Moore's law, because we have made the transistor smaller to put more and have more of that complexity per chip. But the point is that what he was thinking was not about speed, it was about the complexity and the number of devices. If we can put more devices on the chip, we can make memory chips that have more memory per die. So DRAM capacity, or for dynamic random access memory capacity about 4x every 3 years. Now it's more about doubles every 2 years, but as we'll see, the DRAM is not just transistors, it also holds the, the data in capacitors. So it's not strictly a transistor type of circuitry. It has capacitors, so that makes it, that skews what we get a little bit. And because of that, because we're storing the bit in a capacitor, it doesn't, you don't gain the speeds that you get with just pure logic, like processor digital logic. You get about 1.x speed increase every 10 years. And then, which is important, the cost per bit decreased about 25% per year. So that means that roughly every 4 years, I can afford, for the same amount of money, I can afford 4 times the amount of memory. So that definitely is important, because the more memory I have, my programs, which is what I care about from a user perspective, can increase in complexity. And I can do more sophisticated applications. Let's not forget about the disk. The disk is an important part of a computer system. The disk has increased about 60% per year. That is a very, very nice. Now, usually what happens is that the price of the disk doesn't change. You just get more for the same price. And that's the way that stayed for many, many years. In the context of processors, when we talk about clock cycle, we're simply talking about the reciprocal of the clock rate. So the clock cycle is the period of time between similar edges of a rectangular wave type of clock, and the clock rate is simply the clock frequency. So for example, if you have a 500 megahertz clock rate, that means that you have a 2 nanosecond clock cycle. For 1 gigahertz, that's 1 nanosecond clock cycle, and so on. So 4 gigahertz, 250 picoseconds, that's pretty short time, right? We're going to see that you're not doing in that period of time, 250 picoseconds, you're not doing anything that is really that meaningful. It's really through the pipelining and the parallelism and the aggregate of how you execute the instructions that you get your actual workload done. And that's why it's so important to understand good architecting, so these processors can be architected for performance. Now let's talk about machine organization, or processor or computer organization. Pretty much any computer can be divided into these 5 parts. You're going to have some type of input devices, and that's how the system communicates with the users and reports to the user. Then you have memory. So memory is used for program and data. And when we talk about memory, we are talking about memory in a very broad sense. We are talking about anything that can store, any type of a storage or mass or block storage type of device on the system. You were talking about the disk. We can be talking about a solid state disk with flash. We can be talking about DRAM. We can be talking about SRAM on the actual chips and the different levels of cache. So we're talking about everything that we can use as a bulk storage for both program and data, including the operating system, which is a special type of program or collection of programs. Then we have the data path, and the data path is what actually transforms the data under the direction of the program. So the data path is managed by the program, but it acts on the data and produces modified data. The controller is what interprets the program and tells the data path exactly what it needs to do. So it manages the data path exactly. And last but not least, we have the output devices to get the data back to the outside world. Okay, so like a screen. So that's a simplified view, but that gives you an idea. Specific to the course, we're going to be talking a lot about the CPU, control and data path. And then in chapter 5, we're going to talk about memory and hierarchy of memories. This we're not going to talk so much about them because it's very heterogeneous. You have many types of inputs and output devices. We may mention some general characteristics of it, but for example, you can have a course just on disk drives, which is a memory device, but also has an input-output characteristic to it. You could do a course on computer monitors and flat screen type of technology. So we're going to be talking mostly about this, and we have a very detailed chapter on memory hierarchy. Now this is a budget based on heuristics that you can use just to give you an idea. If you're going to design some type of computing device, 25% is for the processor. So like, if you buy a Dell laptop, 25% is for that processor module, and it may not be just a chip. It may be a module that has its own cooling subsystem associated with it. So it could be a very sophisticated type of part. And then you have the memory. The memory is another 25%. For minimum memory size, if you want to expand on that, then that costs you more. And then the 50%, the rest or the 50% of the system is everything else. That gives you a rough, place to start from a budgeting perspective for a computer system. Now, one of the things that if we get to it, we'll because we have so many things to cover and we have to cover the fundamentals that if we get to it, maybe we can mention some things about multicore. But multicore is the ability to just put more processors on a single chip. So it's a testament to that increasing of complexity as predicted by Moore's law. We're going to be really talking about the single processor, but you need to be aware that the way that, since we have the ability to put multiple cores, because we can put so many devices on a single chip, that's one reason all processors are multi-core these days. But the main reason that we have multi-core processors is because we are not making them faster from a clock rate perspective. Clock rate or frequency is directly proportional to power dissipation. And there was a time where around 3 gigahertz, these chips were getting so hot beyond 100 watts. And if you touch a 100-watt light bulb, you know how hot that is. That it was being difficult to remove effectively that amount of heat from the processor. Not only a drain on battery life, but also a reliability concern. So how can we get more performance if we are not increasing the frequency? Well, one way is just to put more cores. Run them at a lower speed, save power, but now since Moore's law affords us that we can put more and more devices on these chips, let's just put more cores. That was the main reason behind the proliferation of multi-core. Was a way to sort of, by design, stagnate the increase in frequency to tame the power dissipation, but then try to increase the performance by having multiple processor cores. And that really brought an interesting problem, which is how you use effectively the cores by the software. So sadly, a lot of software doesn't make use of multiple cores effectively. And you can run some software and watch the performance management software that is part of, let's say, your Windows 10 operating system, and you can see the load for multiple cores, and you'll see that most of the work is being done by a single one. They are not being used effectively. And how to program for parallel processing is still a very rich area for improvement these days. So you have to be aware of that. And in the context of what we're going to be talking about. So, for example, a recent cell phone has 4 cores on the processor chip. This Cortex, they refer to ARM cores. And there is another one, so up to like 4 cores of the Cortex A53, which refers to a specific version of the ARM processor core or ISA. So another conceptualization tool that we're going to be using is hierarchy. Goes hand in hand with abstraction, because hierarchy allows us to decompose a system into subsequent levels, and we can call them subsystems up to a point that we don't need to go any further down, and we can call them components. Now, a component on a system, if I'm talking at some level of abstraction, is one instance of that decomposition. So if I'm talking at a specific level of abstraction, I'm talking about a system, and here I have this identified as a component, and I can do my work. If I can learn, work, teach, at that level with that decomposition, great. But in another setting, that component is a system that has itself subsystems. So if I'm just talking about that as a system, then I need to keep going down and deeper. For example, we already talked about it. We talked about computer system, and we have a disk. A disk is a component of a computer system. But the disk is a very complex system itself. In the context of the computer system, it's just a component. But if I am a hard disk manufacturer, my system is the disk, and it has subsystems. It has preamplifiers for the read channel. It has the read channel itself. It has the servo part. It has the storage. It has the bus interface. All these are subsystems of the disk if I'm talking about the disk as a system. But if I'm talking about computer systems, and I don't care for this details about disk drives, the disk to me is just a component. So hierarchy and abstraction are tied together, and that is also shown here in this dichotomy of hierarchies of having your application software running on top of the system software, and that system software is running on top of the hardware. That is one level of hierarchical view of and a way to abstract the use case of any computer system. This is a great representation of what hierarchy can do and how you get more detail and information as you go down in the hierarchy from a level of abstraction perspective. But that information could be superfluous if we don't need it. So at some point we need to say, this is how far we go with our abstraction and work at that level. But every level that you go down, you have more information and things get abstracted up. So this is a nice example because it shows a segment of a high-level language, specifically in C. So let's say that you have a function. Now this function is called swap, and what it's doing is swapping two members of an array. So if you give it a pointer, this is a pointer to an array, and you give it an index into that array, given by k, is essentially going to swap v of k and v of k plus 1. So if v of k was 2 and v of k plus 1 was 3, after you run this, v of k is going to be 3 and v of k plus 1 is going to be 2. So you can see how it's implemented. So we have a temp integer. So that temp gets the value of v of k. V of k now gets v of k plus 1, and now v of k plus 1 gets temp. And there you have the swap. These things could be used in something like sorting algorithms. So this is in C. Now, how would that be expressed, let's say, in assembly language in the ARM V8 ISA, which is what we're going to be using in this course? Notice that in here, other than the fact that I'm doing a swap of two members of an array, I don't know a lot more than that. And that may be great if I'm just thinking about the algorithm, and that's all that I need to know. Now here in assembly, other things are happening. First, I have a shift of 3 bits for something that is coming into a register, and then I'm adding that or I'm adding that to another, something that came into another register, x0. And now I'm doing a couple of loads and a couple of stores. And this is where the swapping is happening. So basically, I'm getting this from this location and putting it in this register. And then I'm getting this from 8 bytes later. I'm putting it in this register. And then I'm storing what I got from the 8 bytes later into the one where this is 0, and what I got from the 0 displacement into the 8 displacement. So we'll go through things like that in a lot of detail in chapter 2. But what I want to highlight is that here you're having to displace 8 bytes. That tells us more information. It tells us that the word size of this arm, or the not the word size, but the data as represented by an integer is 8 bytes or 64 bits. Therefore, the data path needs to be 64 bits. I can infer from this that this core has a 64-bit data path, 64-bit wide. So the added is 64 bits. Everything on the data path side is 64 bits. If I looked at the machine language for each of these instructions, I could get something like this. And these are 32 bits. So now I know that the word size for the program is 32 bits wide. Not only that, if I had the information, since these are the instructions, okay, here we have 7 instructions. Here we have 7 instructions. If I had the instruction map for this core, I could tell from this actual ones and zeros how many registers this core has, how many instructions maximum it has, because I could look at the width of the opcode and the width of the registers and a lot of other fields. So if I had the mapping of the fields in the instruction and I looked at these instructions, I could tell a lot more about this core. Frankly, over here, I cannot tell anything about the specific hardware. So this illustrates that abstraction, as you go down in the level of abstraction, you get more information. At the same time, again, you may not need that information, so you need to find the right level of abstraction. And we're going to be doing that throughout. All right, so this is kind of a summary of this part of the chapter. Things that you need to remember, okay? The different classifications of computers. They're different, but they are the same in many ways. They all have input and output. They have storage devices. They connect to the network. And the post-PC era, remember, tablets, different types of touchscreens, resistive, capacitive. So you're used to seeing the capacitive types. You can get more resolution with capacitive types, and you can support multiple touches and very complex type of touch and swipe and gesture patterns. So most tablets and smartphones use capacitive type of touchscreens. However, you have to touch them with your bare hands. So for industrial applications where people have gloves and things like that, that you have to use resistive types, which really you don't have to touch with your bare hands. It doesn't rely on the field, the electric field that you provide by touching it yourself with your hands. Uh, it actually relies on a different mechanism that is related to the touch, how hard you tap it. LCD screens, so basically you have the different colors represented by different pixels. So again, we're not going to be talking a lot about I/O type of devices like screens that you could, again, have a course about video and things like that. Some interesting pictures of some devices. So here you have, the actual PCB and how it there is some flex connections on the PCB. Some interesting pictures of some devices. So remember, things to remember: data path performs the operation on data, transforms the data. Control, it manages the data path and as instructed by the program. A very important concept, cache memory, which we have chapter 5 devoted to that, is a way to take advantage of our ability to predict which parts of code and data are used the most and the most frequently. So we're going to talk about those concepts in chapter 5. Some nice pictures of processors. So now this different 2-on cores. So here would be the control section and data paths. DRAM interface to interface to the actually, sorry, this would be DRAM interface over here to interface to object DRAM and some other miscellaneous logic. You have a video DAC here to drive the display. So a DAC is a digital to analog converter. You have the Wi-Fi radio over here, the Wi-Fi port, and the audio section over here. So you get an idea that this is the Apple A5 core. And some others by comparison, the A8 and the A7. Notice when we get to A7, now we have 2 CPUs, but now we have 4 GPUs on the same chip. That's just 6 processors. There is these areas over here that are shared memories, and this is a level 3 cache that when we discuss in chapter 5 memory hierarchies, you're going to understand level 1, level 2, level 3, DRAM, disk, the whole hierarchy. But a lot of and more of the functionality is being integrated on the same chip. So people look at these chips and take pictures, and they publish them. And these are molded in plastic, so you have to use acid to actually remove the plastic, and sometimes you eat into the chip itself. That's what this is. This is actual damage from decapping the chip to look at it. So there are companies that basically that's what they do, like Chipworks. More pictures. Here we have 4 cores of GPUs, dual CPU. This is the A8 processor. You can see that it's the same theme. You have GPUs, you have CPUs. So 2 CPU cores in A9. Now you have 3 sets of 2 GPU clusters. So that is 6 GPUs and 2 CPUs, a total of 8 processors on a single chip. And you can see the level 2 cache over here, which the way that is floor planned is common to both cores, so it may be shared by both cores. That means that each core will have its own level 1 cache, and so on. So you can imagine the number of transistors, and that's how we get to billions of transistors. All right, so just to reiterate and remind you, abstraction helps us deal with that complexity. We hide the lower level of details. Instruction set, very important. Going to talk about instruction set a lot in chapter 2. That's how we abstract. That's how we abstract that processor to the programmer. We tell the programmer, this processor, no matter how complex it is, and no matter how we have implemented that complexity, it performs this set of instructions. Go write your program using these instructions and you'll be fine. And hey, the programmer doesn't need to deal with any of this. All she knows is that if the right stream of instructions is fed, it's going to happen in the most efficient and the fastest way possible. So it does that interfacing for us by hiding the implementation. The main things here are abstraction and instruction set architecture. All right, some pictures of some things that we have discussed. Just pictures. Network stuff. All right, this I love this because it gives you an idea, at least up to the year 2013. So the vacuum tube, if we measure, we go back to 1951, and we normalize performance and cost, the ratio of performance per unit cost, and we normalize that, and we say that in the era of the vacuum tube, that was 1951, and we start projecting and figuring out this ratio as in 1965, when the pervasive technology was transistors. Then in the mid-70s, the integrated circuit was fully commercialized. 1995 and beyond, VLSI and UVLSI eras. These are the increases times in the relative performance per unit cost of the technology that has been enabled, by what Gordon Moore was talking about. So this is a mere, what, 60 years. Can you think of anything else that has improved 250 billion times in 50 years? Nothing has improved this much. Fuel efficiency hasn't improved this much. Quality of healthcare has not increased this much. There is nothing that you can think that has increased this much in 60 years, in any period of history. So this is truly amazing, and that's why we have the ability of the technology that we enjoy. So the underlying reason is that in reality, the raw materials for doing this is very inexpensive. Silicon, of which we have an abundant supply because we make it from sand. And if we don't have sand, we can make sand if we find the right type of rock to pulverize. So yeah, very inexpensive, the raw material, silicon. Now the process is expensive, it's complex to turn that silicon into semiconductor devices, but the actual cost of the raw material, the silicon, is very inexpensive. So I'm going to stop here, and we'll pick that up. Next on Thursday, and we'll keep going through the chapter. I want to stop here and see if there are any questions. Okay.